good morning. So we'll continue with having a look at the Poisson brackets, and then later today we'll move on to the final topic of this course, namely Hamilton Jacobi theory. But let me just briefly recap the main result from yesterday and make a clarifying remark. So using the very definition of Poisson brackets, we were able to derive the following equation for an arbitrary function f, depending on the canonical variables q and p. And so we stated that if f is a constant of motion, then that would be equivalent to the Poisson bracket here vanishing. However, it's here I have to make the clarifying remark, namely that f being a constant of motion is more generally defined as the total time derivative of f vanishing. So we see then that f being a constant of motion is only equivalent to the Poisson bracket vanishing if, in addition to this, there is no explicit time dependence in f. So I probably didn't emphasize this sufficiently in the lecture yesterday. So the point is just that if f is a constant of motion and it has no explicit time dependence, then the Poisson bracket vanishes. And we ended yesterday, I believe, by considering an example of how these Poisson brackets could be used for the angular momentum, using the components of the angular momentum vector and momentum. And we had found that the following equation would be valid, where these are the components of the ordinary momentum, the components of the angular momentum, and epsilon ijk is the Levi-Civita tensor. Now, we derived this result in a particular way. We just inserted, we did this component for component. We considered some specific examples, such as py, lx, etc. But we could actually have derived this result very compactly by using immediately the definition of a cross product in terms of the Levi-Civita tensor. And this is something we learned how to do at the very beginning of this course, I believe. So let me just briefly show you an alternative, very simple derivation of this. So we begin by considering this Poisson bracket immediately without specifying any particular coordinates, such as x, y, or z. Now, the jth component of the angular momentum vector can be written like this by using the Levi-Civita tensor. And you will see precisely this form if you look back to your notes from the beginning of the course. All right, so epsilon here is just a scalar. We can just move it outside the Poisson bracket. So we get the following. By using one of these properties of the Poisson bracket, namely that the bracket of two components of the momentum is 0. So there are in general two contributions from this bracket, one due to the bracket from P and X and one from P and P, but the one from P and P is 0. So this is the only finite contribution. So for this purpose, epsilon and P may be considered as scalars, so we just move them outside. Now this Poisson bracket has a simple form. It's just a Kronecker delta function as we derived yesterday. So we get the following result. And by using now the cyclic permutation properties of the Levi-Civita tensor, that you get sign changes as you permute the indices here, you can write this as follows. So you see here that, so the point with this derivation is just that we can use the Levi-Civita tensor immediately instead of going through the specific coordinates and just get the correct result straight away. Now, using precisely the same type of sort of technical approach, we can arrive at the following relation holds, which is analogous to this relation here. All right. We'll have a look at one more example for how we can use these Poisson brackets, and it's a particularly important example because it's related to group theory, which you will be more familiar with if you take more advanced theoretical physics courses. And the example is to consider the Poisson bracket for the angular momentum components. So for instance, calculating a quantity like this. Now, to evaluate this expression, one possibility, I suppose, could be to insert into the expressions for Lx and Ly the corresponding expression expressed in terms of x and p, like this. So we would have two Levi-Civita tensors and then some product between x and p. That would be kind of messy, I guess, because you would have to permute several different factors. But we can try to alternatively use the very definition of the Poisson bracket instead and see if that helps. So we have this. So to evaluate this expression, we have to find what all of these partial derivatives are. And note that I'm using here the implicit sum convention due to repeated indices. So if we consider this first term initially, we have this from the definition of the angular momentum vector. Now keep in mind that x and the generalized coordinates in the system and the canonical momenta are considered to be independent variables. So the only contribution to the partial derivative here comes from y and z in the case where xi matches this variable. So we get the following. Now we also have derivatives with respect to the canonical momenta, in which case the opposite situation applies. We only get a contribution due to these momenta factors in the case where pi matches px or pz. So we get Kronecker deltas. And we may then apply the same type of consideration for these two last terms. So what we can do now, having obtained these expressions, we can just put them back into here. And what we're dealing with mainly are a couple of sums of Kronecker delta functions. So that's not much more than just doing some bookkeeping for the indices. I'll just give you the final result. We end up with this. And this occurs due to only specific combinations of the indices of the Kronecker deltas contributing to the final result. Now, this was a specific case. We consider Lx and Ly. And I did this to demonstrate sort of how you could proceed to solve the Poisson bracket, but we could have started out right away with general components, Li, Lj and just perform the same type of considerations, we would have obtained a couple of more Kronecker deltas perhaps, but the idea would be the same. So this result may be generalized to the following. So the Poisson bracket of two components of the angular momentum vector will produce a finite result only for a different component, Lk here. If two of the indices are the same, we get 0. Now this result has some significance in terms of group theory. Because there's an important mathematical group known as the Lie group, where we have quantities known as so-called generators that define in a way how this group works, what kind of elements that belong to it. So these generators for a Lie group in general satisfy the following property. So the generators are G. And these coefficients here, C, I, J, K, are known as the structure coefficients. So these angular momentum operators are in fact related to the so-called SO3 group. And the structure coefficients in this particular case are the Levi-Civita tensor, simply. So I just wanted to mention this, but you'll be much more acquainted with this later. Okay, that just about sums it up for the Poisson brackets. I would like to mention one final result. Namely, that the Poisson brackets are invariant under a canonical transformation, meaning that the following relation holds. And this can be shown just from the definition of the Poisson bracket. I believe, if I remember correctly, there's a specific exercise posted on the web which deals with exactly this. And you can even show this explicitly if you want for a particular example. If you recall our treatment of the harmonical oscillator and how we made use of canonical transformations to solve that problem, we initially just made some ansatz for how the transformation should look like and then identified exactly how the transformation would have to be, or how it had to depend on P to be more specific, in order for it to be canonical. We found this. So just by using definitions of the Poisson bracket, you can check explicitly that the bracket is invariant regardless of whether you use the old set of coordinates or the new set of coordinates. Now, in relation to this, I would also like to mention something which is known as Liouville's theorem. That is related also to how the old set and the new set of variables span the same type of phase space as long as the transformation is canonical. So I'll just write down the theorem. Now the phase space of our system is spanned by the coordinates q and the canonical momenta p. And a particular point in this phase space then corresponds to a particular state of the system. Because once we've specified all the coordinates and the momenta, then we have the state of the system. Let me introduce this quantity here, d gamma, as an infinitesimal volume element in this phase space. So it's just the product of all the infinitesimals of all the coordinates and all the canonical momenta. Now what Liouville's theorem states is that an arbitrary volume of this phase space will remain invariant under canonical transformation, which mathematically speaking may be put into the following form. There's an explicit proof of this in the Goldstein book, and I'll just give the main ingredient here, and you can study the proof later on if you want. Now, from calculus, we know that if you perform a transformation of the variables in a multiple integral, in general, the resulting equation looks like this, where D is the Jacobi determinant relating the old set and new set of variables. And the Jacobi determinant is very important to get the correct result. A familiar example of this would be, for instance, going from Cartesian to polar coordinates, where we would have dx dy in 2D then for an area element. Now, if we just forgot about the Jacobi determinant, one might conclude that this should be equal to this. But this is not the case, because we need an extra r here, I believe, which stems precisely from the Jacobi determinant. Now, the point is that you may prove, using Hamilton's equations, that the Jacobi determinant for a canonical transformation is 1. And as I stated, if you're interested in the sort of technical details of this proof, you can consider the Goldstein book. So that concludes the Poisson brackets, and we'll move on to the final topic of this course, which is Hamilton Jacobi theory. And I aim to probably finish this topic in the next lecture, and also give a summary of the complete course in the next lecture. But we'll get started here anyway. Oops. Oh, by next lecture I mean Wednesday, next week. So we'll use the remaining time today to establish the framework for this type of theory. So a little bit about the motivation to begin with. We discussed a bit the previous time the purpose of canonical transformations. And we stated that they serve at least two important purposes. We've written here that canonical transformations may be used to solve mechanical problems, in particular by introducing a new set of coordinates which are cyclic in the new Hamiltonian. So if you recall our discussion the previous time, that was one of the methods or one of the advantages of using canonical transformations. Another advantage would be that we can also recast an unknown form of the Hamiltonian into a more familiar form by using canonical transformations. But oftentimes they're used to find a new set of coordinates which are cyclic, meaning that the equations of motion, the Hamilton equations, will be trivial. So the Hamilton equations, let me just remind you. Look like this. Now, is there any obvious way that we can guarantee that not only one of these coordinates are cyclic, but both of them from this form? So the general aim here is to obtain equations of motions which are as simple as possible. Now the simplest possible case is arguably having q dot equals 0, p dot equals 0. They're just constants. Is there any way we can guarantee that this is the case for the new Hamiltonian? Let me give you a hint. So keep in mind that the original Hamiltonian of our problem and the new one may differ at most by a partial time derivative of a function. where this is an arbitrary function. Well, would you agree that if k is equal to 0, then these equations of motions are pretty easy? Then we just have 0 and 0. So it might sound a bit absurd, but mathematically it's correct. If the new Hamiltonian is 0, then large P and large Q are for sure cyclic coordinates. Okay, fair enough, but how can we get a Hamiltonian which is 0? Well, the idea is to use precisely the freedom of this term. Yes?
Does it make sense to say that the P's are cyclic?
In the sense that the Hamiltonian is independent of them, I guess it does. If we define cyclic in this sense.
But you can't, but do the canonical momenta have canonical momenta of their own?
I guess you could mathematically define canonical momenta of their own. But if we define cyclic, the term cyclic as the Hamiltonian being independent of a variable, then we can say that they are cyclic, right? So in this sense, they are cyclic coordinates. And we can guarantee this by choosing f so that k becomes 0. Okay, so that might seem like a pretty artificial method, but it has some strong advantages. Probably one of the most powerful aspects of this method is that it basically allows us to solve for time-dependent Hamiltonians. Say we start out with a time-dependent Hamiltonian. Then we introduce some appropriate function f so that k here, by construction, becomes 0. Then we have trivial equations of motions, even for a time-dependent Hamiltonian. So if we now use this idea, well, then we have the requirement that k is equal to 0. So we have the following equation. And for our purposes, it is convenient to choose the second class of generating functions. So as a reminder, we can recall that there are in general 4 generating functions because they need to depend on one old and one new variable. And it's also the generating function itself that enters here. So for reasons that will become clear in a little while, it's convenient for our purposes to choose the second class, in which case the generating function depends on the original coordinates and the new canonical momentum. We may also recall that for each generating function, we had 3 characteristic equations that defined the canonical transformation itself. So we had 2 equations relating the old set and the new set of variables, and one final equation of precisely this form. So the first of the equations defining the actual transformation for the second class of generating functions looks like this, if you consult your notes. And it's a convention in the literature to use S instead of F2. So we're just changing the notation from F2 to S. So the final equation that we end up with having to solve is the Hamilton Jacobi equation. So we'll continue with this after the break.